The learning outcomes. Define Pythagorean triples. Recognize the history of Pythagorean relationship. Explain the different ways of constructing Pythagorean triples with clear understanding. Analyze the different lemmas and theorems that supports the concept of Pythagorean triples. Solve problems related to proving Pythagorean triples using the learned concepts, lemmas, and theorems.
Hi, what's up? I am Julia Mitaladua and we will talk about the Pythagorean triples. Now, what is a Pythagorean triple? Well, a Pythagorean triple consists of the three positive integers a, b, and c such that a squared plus b squared is equals to c squared. Pythagorean triples are any three positive integers that are completely satisfy the Pythagorean theorem. Now, as I said earlier, the Pythagorean theorem states that in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the two other legs. Now, the three sides of the right triangle form a Pythagorean triples, such that the triple is commonly written as ABC, and a well-known example is 3, 4, 5, which is the smallest Pythagorean triple. Now, if ABC is a Pythagorean triple, then we say that it is a primitive Pythagorean triple if and only if ABC have no common factors, which is GCD of A and B is equals to the GCD of A and C is equals to the GCD of B and C, which is equals to 1. Now, a primitive Pythagorean triple, or a PPT for short, is a triple of numbers ABC such that ABC have no common factors other than 1 and satisfy a squared plus b squared is equals to c squared. Note that 3, 4, 5 is a Pythagorean triple. Moreover, for any positive integer n, we have the quantity of 3n squared plus the quantity of 4n squared is equals to 9n squared plus 16n squared is equals to 25n squared is equals to the quantity of 5n squared, such that 3n, 4n, 5n is also a Pythagorean triple. Thus, there are infinitely many Pythagorean triples. Now let's proceed to the history of Pythagorean triple. Now, the Pythagorean relationship was known even before Pythagoras. One of the Babylonian clay tablets in the G.A. Plimpton collection at Columbia University indicates that the Babylonians knew of the Pythagorean theorem more than 3,500 years ago. Now, the study of these Pythagorean triples began long before the time of Pythagoras. There are Babylonian tablets that contain lists of parts of such triples, including large ones indicating that the Babylonians probably had a systematic method for producing them. Even more amazing is that the fact that the Babylonian may have used their list of Pythagorean triples as primitive trigonometric tables. Pythagorean triples were also used in ancient Egypt. For example, a rough and ready way to produce a right angle is to take a piece of string, mark it into 12 equal segments, tie it into a loop, and hold it in taut in the form of 3, 4, 5 triangle. Now, this provides an expensive right angle tool for use on small construction projects such as marking property boundaries or building pyramids. I think that would be all for the introduction and the history part of the Pythagorean triples.
Good day, everyone. I am Larilyn Asla Bastilla, and I am going to discuss the ways on how to construct a Pythagorean triples. So, what are the ways to construct Pythagorean triples? first we have is using the Fibonacci numbers. Next is if n is any odd positive integers, and if n is any positive integers, Wiley and Kennedy method, and lastly, the Euclid method. So first, we're going to discuss using Fibonacci numbers. So we can use the Fibonacci numbers. We have here the table f sub 0, f sub 1, 2, 3, 4, until 8, until so on and so forth. So under the f sub 0 is 0, f sub 1 is 1, and f sub 2 is 1, f sub 3 is 2, 3, 5, 8, 13, 21, 21, and so on and so forth, where each term in the sequence is the sum of the previous two terms. To construct Pythagorean triples as follows. So, we can see here in f sub 0 is 0, f sub 1 is 1, and in f sub 2 is 2. So, in the sequence is the sum of the previous two terms. So in f sub 1 0, f sub 0 is 0. So 0 plus 1, these are the two previous terms in f sub 2. So 0 plus 1 equals 1. And in f sub 3 is 2 because its two previous terms is 1 and 1. So 1 plus 1 is 2. And it will become in f sub 4, it is 3 because the previous two terms is 2 plus 1, which is 3. So next we have is let n be a positive integer and define. So a equals f sub n plus 3, b equals 2 f sub n plus 1, and f sub n plus 2. C is f sub 2 plus 1 plus f sub 2 plus 2, where f is the nth Fibonacci number. Then it is easy to show that a squared plus b squared equals c squared. So that ABC is a Pythagorean triple. As an exercise, determine if it is a primitive Pythagorean triple. Also, show that we cannot generate all Pythagorean triples in this way. So how can we say that it is a primitive Pythagorean triple? If the three natural numbers, the a, b, c, is a prime number, so we can say that it is a primitive Pythagorean triple. Next way is if n is any odd positive integer. Another method discovered by the Pythagoreans is as follows. If n is any odd positive integer, and we define a is equals to n. For b, it is n squared minus 1 over 2. And for c, n squared plus 1 over 2. Then, ABC is a Pythagorean triple. Verify this as an exercise and show also that we cannot generate all Pythagorean triples in this way. And next way is if n is any positive integer. Yet another method discovered by the Greek philosopher Plato is as follows. If n is any positive integer, and we define a equals 2n, b equals n squared minus 1, and c is equals to n squared plus 1. So this is for n is any positive integer. Next method is the Wiley and Kennedy method. In 1934, M. Willie and E.C. Kennedy gave the following method for generating infinitely many Pythagorean triples. So we can see here the table A, B, C. So this is the Willie and Kennedy method. You are invited to find a formula for this A, B, and C and show that it does not indeed generate infinitely many Pythagorean triplets, but again, not all of them. The last method we have is the Euclid method. In his book, The Elements, Euclid gave the following method for generating Pythagorean triplets. For any positive integers, m and n, which are relatively prime, that is GCD mn equals 1, and of different parity, this is one is even and the other is odd. If we define for m is greater than n. So we have here A is equals to 2mn, and for B, m squared minus n squared. For C, we have m squared plus n squared. Then ABC is a primitive Pythagorean triple. Again, primitive Pythagorean triple are the three numbers. The three numbers are all prime numbers. Moreover, every primitive Pythagorean triple arises in this way. In order to prove this, we need the following lemmas. So, the following lemmas will be discussed by our next reporter. And that's all for my report. I hope you have learned. Thank you.
Good day everyone. In this video, I will help you analyze the different lemmas and theorems that supports the concept of Pythagorean triples. And this is the continuation of Miss Labastilia's topic, which is the ways to construct Pythagorean triples. Lemmas to be considered in Pythagorean triples. So the first lemma is if A, B, C is a primitive Pythagorean triple, then A and B are of different parity. It's either the other is even or the other is odd. And the second lemma is if U and V are relatively prime positive integers such that U times V is a perfect square, then both U and V are perfect squares also. So the proof of the first lemma is if A and B are both even, then the GCD for A and B is either greater than or equal to 2, which is a contradiction since A, B, and C is a primitive Pythagorean triple. And if A and B are both odd, then A squared is congruent to 1 modulo 4 and B squared is congruent to 1 modulo 4. So that C squared is equals to A squared plus B squared is congruent to 2 modulo 4, which is impossible since the square of any integer is congruent to 0 or 1 modulo 4. Therefore, A and B have opposite parity. So the proof of the second lemma would be let P be a prime that divides U and let A be the exact power of P in U. Since U and V are relatively prime, then P does not divide V. However, U times V is a perfect square, so that A must be even. Since this holds for all primes P dividing U, then U is a perfect square Similarly, v is a perfect square also. So another theorem states that if A, B, and C is a primitive Pythagorean triple with B, which is even, then there exist positive integers m and n which are relatively prime and opposite parity, with m is greater than n such that A is equals to m squared minus n squared, B is equals to 2 times n, and C is equals to m squared plus n squared. So the proof would be, if A, B, and C is a primitive Pythagorean triple with B, which is even, then A is odd. And since C squared is equals to A squared plus B squared, then C is also odd. Therefore, C minus A and C plus A are both even, so that it satisfies this equation C plus A over 2 times C minus A over 2 is equals to B over 2 squared. Any common divisor of the two factors on the left divides both of their sum C and their difference A. And since the GCD of A and C is equals to 1, then the two factors on the left have no common divisors except 1. That is, they are relatively prime. From the lemma, they must be both squares, so there exist positive integers m and n such that it satisfies the equations C plus A over 2 is equals to m squared, and C minus A over 2 is equals to n squared, and B over 2 is equals to m times n. So we note that m and n are relatively prime since C plus A and C minus A are relative prime also, and that m is greater than n. Also, since C squared is equals to m squared plus n squared, and C is odd, then m and n have different parity since our C is odd. So, example. So the square of 3 is 9 is the difference between 16, which is the square of 4, and 25, which is the square of 5, giving us the triplet 9, 16, and 25, and 7, 24, and 25. Similarly, the square of 5, which is 25, is the difference between 144, which is the square of 12, and 169, which is the square of 13, giving us the triplet 5, 12, and 13. So those are the lemmas to be considered in Pythagorean triples. So to learn more, let's hear Mr. Malesa's Pythagorean triples problem. So that would be all. Thank you for listening.
Hello everyone, good day. This is Cal Christian Malesa, and now let's proceed to the Pythagorean triple problems. So we have here two examples. Now let's start with example number 1. Prove that quantity 5, 12, 13 is a Pythagorean triple. So we have here the solution. To prove that quantity of 5, 12, 13 is a Pythagorean triple, so we know that the Pythagorean theorem formula is a squared plus b squared is equals to c squared. So we have here the quantity of a, b, c is equals to quantity of 5, 12, 13. So now that we have already found the values of the variables a, b, c, so we will just simply substitute the the values of the variables to the given formula. So we have here 5 squared plus 12 squared is equals to 13 squared. So now let's simplify. So we get 25 plus 144 is equals to 169. Adding 25 plus 144, we get 169. So we have here 169 is equals to 169. Hence, the given set of integers satisfies the Pythagorean theorem. Quantity 5, 12, 13 is a Pythagorean triple. So now, let's proceed to example number 2. Check if quantity of 7, 15, 17 are Pythagorean triples. So we have here the solution. Quantity of A, B, C is equals to the quantity of 7, 15, and 17. We know that the formula of the Pythagorean theorem is A squared plus B squared is equals to C squared. So now that we have already obtained the values of the variables, so we will just simply substitute the values in the equation. So we get 7 squared plus 15 squared is equals to 17 squared. So by simplifying, so we get 49 plus 225 is equals to 289. So adding 49 and 225, we get 274. Thus, 274 is not equal to 289. Hence, the given set of integers does not satisfy the Pythagoras theorem. Quantity 7, 15, and 17 is not a Pythagorean triplet. Also, it proves that the Pythagorean triples are not made up of all odd numbers. So, I think that's all for my part about the Pythagorean triples problem. So I hope that you've learned something from our discussion. Thank you so much.
Good day, everyone. Allow me to introduce myself. My name is Teacher Mary Maxine Magan, and you can call me Teacher M. For today's topic, I will going to discuss about the concept of sum of squares. Anyone who knows about the concept of sum of squares? To further give you information about it, I will discuss to you later on. But before anything else, I will give you the learning outcomes. First, describe the meaning of sum of squares. Next, examine and compare the various square sum theorems. Third, calculate sums with accuracy. And lastly, apply the formula for the addition of squares of numbers. Now, let's proceed for the definition of sum of squares. Sum of squares refers to the sum of the squares of numbers. It is basically the addition of squared numbers. So literally, sum of squares is derived from its name itself, which is to sum the squared numbers. The process is adding the squared numbers. To continue, the squared terms could be 2 terms, 3 terms, or n number of terms, first and even terms or odd terms, set of natural numbers, or consecutive numbers, and etc. In arithmetic, we often come across the sum of n natural numbers. There are various formulae and techniques for the calculation of the sum of squares. Let us write some of the forms with respect to 2 numbers, 3 numbers, and n numbers. First is the sum of two numbers x and y, which is in the form of x squared plus y squared. Another is the sum of three numbers x, y, and z, which is in the form of x squared plus y squared plus z squared. Another is x sub 1 squared plus x sub 2 squared plus so on plus x sub n squared, which is the sum of squares of n numbers. Sum of squares theorems are theorems in additive number theory concerning the expression of integers as sums of squares of other integers. For example, 30 is equal to 1 squared plus 2 squared plus 5 squared. So 30 can be expressed as a sum of 3 squares. Let us evaluate 30, which is equal to 1 squared plus 2 squared plus 5 squared. If 1 squared is equal to 1 plus 2 squared is equal to 4, so 1 plus 4 is equal to 5. And lastly, 5 squared is equal to 25. So 5 plus 25 is equal to 30. So 30 can be expressed as the sum of 3 squares. However, there are numbers that cannot be expressed as sum of 3 squares like 23. So sum of squares theorems gives Fermat-like ways to differentiate which numbers can and cannot be expressed as sums of squares. Sum of two squares. So, shown here is the list of the integers from 0 to 100 that can be written as a sum of two squares, organized in two sets of 4 columns with spaces marking integers that are not equal to the sum of two squares. So shown in the picture, you must remember and bear in mind that numbers class, since it will help you to find the sum of two squares. That would be all for the introduction of sum of squares. This is Teacher M, and now I will give you the floor to Teacher Jess.
Hello, Best Edma 3. Welcome to our class. I am your teacher Jess, and now we're going to discuss about Fermat's theorem on the sum of two squares. So in the case that k is equals to 2, add prime p is expressible as a sum of two squares if and only if p is equals to 4n plus 1 for some positive integer n. So for add prime p, there exists x and y such that x and y is an element of integer p is equals to x squared plus y squared if and only if p is congruent to 1 modulo 4. Now let's have the theorem 1.28.1. This is the sum of two squares. So a positive integer n is equal to the sum of two perfect squares if and only if the prime factorization of n contains no odd exponent on any prime that is congruent to 3 modulo 4. So for example, odd primes 5, 17, and 41 are all congruent to 1 modulo 4. Why? As predicted by Fermat's theorem on the sum of two squares, each can be expressed as a sum of two squares. So based on the example, the 5, 17, and 41, we have 5 is equals to square root of 1 plus the square root of 2. We have 17 is equals to the square root of 1 plus the square root of 4. In the 41, we have the 4 squared plus the 5 squared. So on the other hand, add prime 7, 19, and 31 are all congruent to 3 modulo 4 and cannot be expressed as the sum of two squares. So now let's proceed the sum of squares formula for two numbers. So the formula for addition of squares of any two numbers x and y is represented by x squared plus y squared equals to x plus y squared minus 2ab, where x and y are real numbers. So we have here the proof. So from the algebraic identities, we know that x plus y squared is equals to x squared plus y squared plus 2ab. Therefore, we can write the above equation as x squared plus y squared is equals to x plus y squared minus 2ab. Now let's proceed to the sum of three squares. As we did in the previous section, let's start by listing the non-negative integers that are at most 100 and able to be written as a sum of three squares. Recalling previously that 7, 15, and 23 could not be written in this way, so we put our list in 8 columns. So as you look at the table, here are the patterns. So we see no number that is congruent to 7 modulo 8. And the only other missing numbers belong to fourth column where they are 28, 60, and 92. So these numbers are each 4 times a number that is congruent to 7 modulo 8. And the last observation suggests that, again, factorization of a number may make a difference in expressibility as a sum of squares. And that would be all. Now let's proceed to Teacher Kim.
Hello BS Ed Math 3, welcome to our class. I am Teacher Kim and I will be discussing Legendre's 3-square theorem. So in the case that k is equal to 3, Legendre's 3-square theorem says that a natural number n is expressible as a sum of 3 squares if and only if n is not equal to 4 raised to the power of a times the quantity of a times b plus 7 for integers a and b. So formally, Legendre's 3-square theorem says the following. For n, an element of natural numbers, there exists x, y, and z, an element of integers where n is equal to x squared plus y squared plus z squared. If and only if there doesn't exist a and b, an element of integers where n is equal to 4 raised to the power of a times the quantity of a times b plus 7. So for example, 13, 26, and 41. These numbers cannot be expressed in the form of 4 raised to the power of a times the quantity of a times b plus 7 for some integers a and b. So as predicted by Legendre's 3-square theorem, each can be expressed as a sum of 3 squares. So for 13, we have 0 squared plus 2 squared plus 3 squared. For 26, we have 1 squared plus 3 squared plus 4 squared. And for 41, we have 3 squared plus 4 squared plus 4 squared. So on the other hand, brute force will reveal that for 15, we have 4 raised to the power of 0 times the quantity of a times 1 plus 7. For 28, we have 4 raised to the power of 1 times the quantity of a times 0 plus 7. And for 92, we have 4 raised to the power of 1 times the quantity of 8 times 2 plus 7, which cannot be expressed as a sum of 3 squares. So now let's proceed to the sum of squares formula for 3 numbers. So the formula for addition of squares of any three numbers, say x, y, and z, is represented by x squared plus y squared plus z squared is equal to the quantity of x plus y plus z squared minus 2xy minus 2yz minus 2xz, where x, y, and z are real numbers. So for the proof, from the algebraic identities, we know that x plus y plus z raised to the power of 2 is equal to x squared plus y squared plus z squared plus 2xy plus 2yz plus 2xz. So therefore, we can write the above equation as x squared plus y squared plus z squared is equal to the quantity of x plus y plus z raised to the power of 2 minus 2xy minus 2yz minus 2xz. So that's all. Now let's proceed to Teacher Jenny for discussing another topic. Thank you.
Hello BSed Mathematics 3, so this is your teacher Jenny. Now we are down to the last theorem in getting the sum of squares. So as a recapitulation, we were being introduced to the different concepts in getting the sum of squares by teacher Maxine, and then it was followed by the Fermat's theorem on the sum of two squares by teacher Jessa, and then the Legendre three-square theorem by teacher Kimberly, and now we are down to the last theorem to be discussed by yours truly, which would be the Lagrange four-square theorem. So I hope you guys are excited to dig further and to learn more about it. So Lagrange four-square theorem, I know that some of you here are already familiar with it, but also some are not yet. So without further ado, let's get it started. Alright, so Lagrange four-square theorem. So it is also known as Bachel's conjecture. And in the case that k is equal to 4, every positive integer n can be expressed as sum of four squares. So formally, this theorem says that it says that for n as the element of natural numbers, there exist the integers a, b, c, d such that n is equal to a squared plus b squared plus c squared plus d squared. So a, b, c, d are the integers that we need to square and we need to sum up. Alright, so we have here a proof with a proof for this formula. So let n be any positive integer, and if n is equal to a squared plus b squared plus c squared for integers a, b, and c, then n is equal to a squared plus b squared plus c squared plus 0 squared. So if n cannot be written as the sum of three perfect squares, then n has the form 4 to the power of k quantity 8l plus 7 for non-negative integer k and l. So the number 4 to the power of k quantity 8l plus 6 does not have this form, which is the exponent in 2 and the prime factorization is odd, while the exponent in 2 is even and the prime factorization of 4 to the power of k quantity 8l plus 6. So plus 7 if you remember the prime factorization lesson. Thus, there exist integers, namely a, b, and c, such that 4 to the power of k quantity 8l plus 6 is equal to a squared plus b squared plus c squared, and it it would become n minus 4 to the power of k quantity 8l plus 7, which is also equal to 4 to the power of k quantity 8l plus 6 plus 4 to the power of k, which is equal to a squared plus b squared plus c squared plus quantity 2 to the power of k squared. So hence n may always be written as the sum of 4 squares. So this proof has somehow proven that n may always be written in the form, may always be written as the sum of 4 squares. So I hope you have understood what this theorem is trying to convey through this proof. So it justifies that n may always be written as the sum of 4 squares. Alright, so to further understand about this theorem, we will provide some examples. So we have here an example: express 28 as a sum of 4 squares using the proof of Lagrange 4-square theorem. Alright, so we have here, since 28 would be equal to 0 mod 4, and the fourth case applies, so this will be in the form 28 is equal to 4m, which is equal to the quantity 2a squared plus quantity 2b squared plus quantity 2c squared plus quantity 2d squared, where m is 7. Okay. Thus we need to find a, b, c, d that satisfy the statement that states 7 is equal to a squared plus b squared plus c squared plus d squared. And since 7 is equal to 3 mod 4, so we will be applying the third case in the form 7 is equal to 1 squared plus a squared plus b squared plus c squared. Alright, so thus it becomes 28 equals the quantity 2 times 1 squared plus the quantity 2 times 1 squared plus the quantity 2 times 1 squared plus the quantity 2 times 2 squared. So simplify further, we have here 2 squared plus 2 squared plus 2 squared plus 4 squared. Okay, so now let us proceed to tackling about the sum of squares formula for n natural numbers. So in this case, we will be dealing with the formula in getting the sum of squares when it has something to do with the natural numbers. So let us get to know what is natural number. Okay, so the family of natural numbers includes all the counting numbers starting from 1 to infinity. So if you remember, natural numbers are those counting numbers starting from 1 up to infinity. So if n consecutive natural numbers are 1, 2, 3, 4 until n, then the sum of squared n consecutive natural numbers is represented by 1 squared plus 2 squared plus 3 squared plus up until the n squared. Right. So in short, it is denoted by the notation as what is being presented on the screen, the summation of n squared. So the formula for the addition of squares of natural numbers is presented. So as what you can see, it is presented by the summation of n squared is equal to the quantity n times n plus 1 times 2n plus 1 all over 6. So that would be the formula. Now, let's proceed to getting the sum of squares of first and even numbers. So we will be dealing now with those first and even numbers in order to come up with the sum of squares. Right, so it states that the addition of squares of first even natural numbers is given by what is being presented. So the summation of the quantity 2n squared would be equal to 2 squared plus 4 squared plus 6 squared plus 8 squared up until the quantity 2n squared. So as what you can notice, 2, 4, 6, 8 are all even numbers. So that would be the formula. Now, we have here a proof. So of course, in every statement, in every formula, there's always a proof that would justify that certain formula or that certain statement. So we have here the summation of 2n squared, which is equal to 2 squared times 1 squared plus 2 squared times 2 squared plus 2 squared times 3 squared plus 2 squared times 4 squared plus up until 2 squared times n squared. So to simplify it further, we have to factor it out. So the summation of 2n squared is equal to 2 squared times the quantity 1 squared plus 2 squared plus 3 squared plus 4 squared up until n squared. Alright, so simplify it further. The summation of 2n squared is equal to the quantity n times n plus 1 times 2n plus 1 all over 6. Then we have to multiply it to 4. Alright, so the formula, this is the formula for sum of squared and natural numbers, by the way. So we have here the summation of 2n squared is equal to the quantity 2n times n plus 1 times 2n plus 1 all over 3. Alright, so we are done with that part. So now let's go proceed to the sum of squares of first and odd numbers. So this time we are going to deal with odd numbers. So the one that we discussed a while ago was the sum of squares of first and even numbers. So this time we're gonna deal with the odd numbers. Alright, so it states that the addition of squares of first odd natural numbers is given by the formula summation of the quantity 2n minus 1 squared, which is equal to 1 squared plus 3 squared plus 5 squared plus up until the quantity 2n minus 1 squared. So as what you can notice, 1, 3, and 5 are all odd numbers. Alright, now so we have here a proof. So the summation of the quantity 2n minus 1 squared is equal to 1 squared plus 2 squared plus 3 squared up until the quantity of 2n minus 1 squared plus the quantity 2n squared minus the quantity 22 plus 42 plus 62 up until the quantity 2n squared. Alright. So on applying the formula for the addition of squares of 2n natural numbers and of n even numbers, so we will be getting the summation of the quantity 2n minus 1 squared, which is equal to 2n over 6 times 2n plus 1 times 4n plus 1 minus the quantity 2n over 3 times the quantity n plus 1 times 2n plus 1. So it becomes n over 3 times the quantity 2n plus 1 times 4n plus 1 and then minus 2n over 3. Then we have to multiply it to the quantity n plus 1 times 2n plus 1. So taking out the common terms, we get the summation of the quantity 2n minus 1 squared, which is equal to n over 3 times 2n plus 1 to be multiplied to 4n plus 1 minus 2n minus 2. So therefore the summation of the quantity 2n minus 1 squared is equal to the quantity n times 2n plus 1 times 2n minus 1 all over 3, and this is the required expression. So I hope you are able to follow. So after everything, we need to generalize. So we have here the fuse or the summarization of all the formulas to be used in getting the sum of squares. So if we have to get the sum of squares of two numbers, we have a corresponding formula for that. So what is the formula in getting the squares of two numbers? So as what you can see, that would be x squared plus y squared is equal to quantity x plus y squared minus 2ab. Now, if we are to get the sum of squares of three numbers, the formula would be x squared plus y squared plus z squared, which is equal to the quantity x plus y plus z squared minus 2xy minus 2yz minus 2xz. Now, if we are to get the sum of squares of first and natural numbers, the corresponding formula for that is the summation of n squared minus the quantity n times n plus 1 times 2n plus 1 all over 6. Now, if we are to get the sum of squares of first even natural numbers, the corresponding formula for that is the summation of 2n squared equals the quantity 2n times n plus 1 to be multiplied to 2n plus 1 all over 3. And if we are to get the squares of first odd natural numbers, of course, the corresponding formula for that is the summation of the quantity 2n minus 1 squared, which is equal to the quantity n times 2n plus 1 to be multiplied to 2n minus 1 all over 3. Alright, so to understand it further, we will provide some examples that would be in which all these formulas would be applied to. Alright, so we have here some examples. So let's take the example number 1. Evaluate 4 squared plus 5 squared by the help of formula and in answering it directly. So in this case, we will be solving it in two ways, through a formula and through answering it directly as well. Alright, so solution. We know that in this case, 4 squared plus 5 squared, of course, we will be using the first formula, right? So that formula is x squared plus y squared is equal to quantity x plus y squared minus 2ab. So let x be 4 and then y is 5. So let's substitute the value. So that would become 4 squared plus 5 squared is equal to quantity 4 plus 5 squared minus 2 times 4 times 5. So simplified further, 4 squared plus 5 squared is equal to 9 squared minus 40. And then simplified further, that would become 81 minus 40. And the final answer is 41. So in answering it directly, so we have here the given equation. 4 squared plus 5 squared is equal to 16 plus 25, which arrives at the same answer, which is 41. So both answers are the same. The answer when we use the formula and the answer when we have to just directly answer this equation. So hence both of the answers are verified. Now let's proceed to example number 2. So find the addition of squares of the first 40 natural numbers. So in this case, or in this problem, we will be using the third formula. So solution. The formula of the sum of squared natural numbers is given by the formula presented. So the summation of n squared which is equal to the quantity n times n plus 1 times 2n plus 1 all over 6. So here n is equal to 40. So let's substitute it to the formula, to the third formula. So the summation of 40 squared would be the quantity 40 over 6 times the quantity 40 plus 1 times the quantity 2 times 40 plus 1. So simplify further, that becomes 20 over 3 times 41 times 81. Simplified further, 20 times 41 times 27, and then we come up with an answer, 22,140. So therefore, the summation of 40 squared is equal to 22,140. So I guess that ends my part. I hope you have learned something from me when it comes to getting the sum of squares, incorporating the Lagrange 4-square theorem. So this is your teacher Jenny. I hope you have learned something. Thank you very much for listening.